All right, so this is the 5-2, the definite integral. So this is an integral sign. So let's get rolling. So we have a Riemann sum, and that is, adding up the area of a bunch of rectangles, certain number of rectangles. So this is a Riemann sum. This right here is sigma notation, and we use the sigma notation. You probably remember that from last year a little bit, when you're adding up a lot of different sums. So if you have this, a bunch of sums, it would be a little bit easier to use the sigma notation, and you could say I equals 1, and then you'd go to n, however many sort of terms, if you will, that you had to add up. And then definite integral is basically, so this is what an integral is. If you let the limit, as I talked about yesterday, if you let the limit of your number of rectangles go to infinity, that will obviously increase the accuracy of the area under the curve. And if you let it go to infinity, it's actually exactly equal to the net area under the curve. And that's what an integral is. It's the net area under the curve. So it's keeping track of how much is above the x-axis, how much is below the x-axis, and we'll kind of see a little bit of that in the next few sections. But for right now, I'm going to say that it's the same thing as the net area under the curve. All right. So you'll have to probably pause it there. Get that. All right. Just real specifically, the pieces of an integral. So this big, blue is the integral sign. The f of x is considered the function itself. That's considered the integrand, and the dx is just a little operator. It's always there when you write an integral. The b is your upper limit of integration. The a is your lower limit of integration. You'll have numbers here for a and b. So you'll go from 0 to 2, and that means you're finding the area under the curve from 0 to 2, etc. Just like the one I showed on the last notes where I went from 0 to 1, I was finding the area under the curve. Okay, so now let's say we want to figure out the Riemann sum for this particular function, and we're going to use 3 subintervals, so 3 little rectangles. And then we're going to use the right endpoint method to figure it out. Okay, so we're going from 0 to 3. And so let me go ahead and just label this a little bit. So here's 1, 2, 3. So 3 little subintervals. And so my intervals would actually be, from 0 to 1, and then 1 to 2, and then, of course, 2 to 3. Okay? And you can tell my interval widths. Remember what we do? We take the 3 minus the 0, and then we divide by the number of subintervals. So number of subintervals is 3. So, we know that the interval width is 1 unit. All right, so let me see if I can draw my rectangles. So I'm using the right endpoint method. So that means I'm using the right endpoints of each of these intervals, and I'm going to take those and plug them into the function. So if I take the 1 and I plug it in, that would be a height of 1, or a height of 3. So I plug in a 1 and I get a height of 3. So what I would do is I would pretend like my rectangle is that tall. And let me back up and actually draw the sketch of this curve. Okay. So this function right here, I could draw the sketch of the curve first, actually. And I would have 0, 4, we know, right? And then this would be, I could plot some points actually. So 1, 3, another good point to plug in would be like plugging in a 2. So that would be 2, 0. And then if I plug in another point, I plug in like 3 into this. So that would be -5. So I knew there was a reason why I went down to -5 here. 1, 2, 3, 4. So down to -5. So 3, -5, so there's another point. And so my graph looks like this. Okay, so better than that. Should be just a normal parabola opening downward. So more beautiful than that, sorry. Now let me back let me go ahead and start doing my subintervals. Okay, so trying to find the area under the curve, so I go from 0 to 1, I use the right endpoint, and then I draw my rectangles. There's one nice rectangle. Then I go to my next interval from 1 to 2, and I'm going to pretend like the height of my rectangle is whatever the y value is when I plug in the right endpoint. So I plug in a 2, I'm like, oh, when I plug in a 2, I get 0. So my rectangle is like, non-existent. Okay, it has no height. That's okay. That's what I use if I'm doing my right endpoints. Then I go to my next interval, 2 to 3, and I plug in a 3 into that, and we already did that. So we found out it was 3, negative 5. So now I'm going to pretend like my rectangle, it has this y value here, and it's actually an upside down rectangle. If it lets me draw my upside down rectangle. Maybe it does. No, it doesn't. So I can draw it with my computer, I think. Come on, little guy. Okay, so it's letting me draw now. Okay, so now I draw a rectangle, and it's actually an upside down rectangle. So what I do is I want to estimate the Riemann sum. So I would say R sub 3 equals, and I would, yeah, let's take a little better. Okay, so I would multiply these together. So I would do my interval width, which is 1. So my interval width is 1. Sorry, it's causing me some troubles. Oh. Okay, so I got interval width of 1, and then each of these y values I would be multiplying by those, so that one would be 3, it's above, and then this one right here at 2, that's a y value of 0, and then that last one actually has a y value of negative 5, so I'd be multiplying by, I have a negative 5 there, and then I would go ahead and simplify this. So this would be 1, and then this would be negative 2. So we actually have a net area under the curve of negative 2 as an estimate using the right endpoint method. And you can tell, there's obviously a bigger rectangle, below than there is above, and so this is an estimate of the area under the curve. It's negative 2. Okay. So that's all you do is just length times height of each of these rectangles, and whenever it's below the x-axis, that's going to cause you to have, it's going to cause you to have negative values. Okay. All right. Express the limit as a definite integral on the given integral, and on the given interval. Sorry. Whoa. Okay. On the given interval. Interval, that sounded funny. Okay. So this is real simple. You don't want to make it crazy hard or anything. Whatever the interval is, then those are going to be your limits of integration. So that would be 0 to pi. And again, when the limit goes to infinity, that just means you're going to be doing an integral. And then wherever you have an x sub I, that just means you're going to have a normal x. So we're going to have x, and then x sub I is just going to be a normal x. So x sine x, and then all your integrals are going to have a dx in there. So you're going to have a dx, and then that's pretty much it. That's how you make it an integral. So that's how a Riemann sum equals an integral. All right, let's go to the next one. The interval is from 0 to 1, so we just go 0 to 1, and then we just are going to write 2, and then this is x sub I squared, so it's just going to be x squared minus 5x, and then we'll put all that in parentheses, and then dx. And there was one piece that I forgot in that top one, and that should be a little change of x. That little change of x is what becomes the dx. Okay? So that each thing is represented or replaced or substituted, however you want to say it. All right, next. Evaluate the integral by interpreting it in terms of areas. Now we're not yet figuring out how to find the full antiderivative and evaluate the integral. But we can do it if it's an exact area of some sort. So as you look at this problem, you would look at this and you go, oh, look at all this area under the curve. And it would be like looks like a semicircle. If, I actually drew it correctly, it would be like a semicircle. And then we have all this area that's under the curve. We say under the curve because it's, like between the x-axis and the actual curve. So it's sort of under the curve as it relates to the x-axis. And so let's say, how do we figure this out? So we would say, if someone asks us, hey, what's the area from 0 to 4, f of x dx, what we would say is that that's pretty much the area of a circle, but it's half of a circle. So that would be pi r squared over 2. And this is actually the radius of this circle would be 2. So we would put that in there. So we have 2 squared divided by 2. And then this would be 4 pi divided by 2. So our area would be 2 pi. And let's try another one. So let's say they ask for the integral from 0 to 6. Actually, let's back up. Let's say the integral from 4 to 6. Integral from 4 to 6 of that particular function. This would equal just a triangle. So this right here, we would say 1/2 base times height. So we'd say 1/2. The base is, it looks like 2 units. And then the height is actually a negative value. So it's -2. So that would be -2. The y value is -2. And then so our final answer for that one would be equal to -2. The last question they could ask about this is they could say, hey, let's kind of put it together. Let's say integral from 0 to 6. So then if we want the integral from 0 to 6, the function, we'd say that equals the area that's above, which would be 2 pi. And then we would subtract the area that we see that's below, or add the areas together if you want to think of it that way. So this would be 2 pi minus 2. Okay. All right, same thing. Let's say we want to evaluate in terms of areas, but they don't give us the picture, they just give us a function. So if you look at this function, very similarly, you might recognize that it's the area of a circle, and it's actually the upper half of a circle. And so, you might recognize, that it's top half of a circle with a radius of 3, right? So let's see if this lets me write again. Okay, so it's finally letting me write again. So we know that this would be, oops, stop letting me write. So I'm going to go ahead and stop there, I think, and maybe finish it up tomorrow. Oh, maybe I'll keep going. All right, so 1, 2, 3, 1, 2, 3. There's the upper half of there's the graph. And if you want to find the area, it'd be the same as the last one, which would be pi. It's really close to this. Alright, so I'll have to finish tomorrow. I'm going to go stop.